Hello friends, welcome back to the bench. Our patient today is a Tough Power series power supply, which doesn't work. Now the reason I ordered it is because I have a few boards coming in next week early, probably on Monday, and our last power supply that we fixed, which only had blown fuse, nothing beyond that as far as I can tell so far at least, but we'll see once we connect the powerful GPU to it. But I already put it in the box, in the case, routed the cables and everything. So this is like working computer. I just need either install Linux or Windows on it, and I plan to install Linux on it and use it as the coding machine, the work machine. We'll see about that. So I need another power supply to test the boards. So I got this one, and we'll see if it's easy fault. I would expect that it's not, because this is relatively new. And the reason is simple. Most faults on these are a result of dry caps. The power supplies are very sensitive to that. A high ESR on the caps, that kind of stuff. But that only happens after a few years of using the device, depending on what kind of caps were installed on it. Now this one is relatively new, so I don't expect this is cap issue. I expect that this is not going to be a simple issue. This is rather going to be something is shorted, or PFC circuit is faulty, or there's a problem with feedback. And if there's a problem with feedback, I had one of these a long time ago that I just couldn't figure out. Everything seems fine. All the measurements are good, but it turns on and off, right? So some feedback issue, right? So let's hope this is not going to be this, and we can actually fix it. Now, as far as my challenge, the coding challenge, I actually finished it yesterday. I'm super tired. I didn't plan on doing it because you have a week to complete it. And if you need time, that's not a problem either. So I didn't have to complete it in one day. But I just kind of started, and there were issues and I wanted to figure them out. And I stayed up till very late hours. Then I couldn't sleep. For some reason, usually I don't have problems with sleeping. I just hit the pillow and I snore as soon as my head hits the pillow. And last night I couldn't. And usually that happens when I do what do you call it? Like very intensive work, and once you spin your brain to the highest velocity, it's kind of hard to shut it down. So that's probably why I forgot to turn on my studio light. There you go. Not that it makes so much difference, but a little. There. But as far as the challenge, it was actually very interesting. There was a lot of gotchas there. They actually seem to be looking for someone really up to the task. The majority is kind of like vanilla PHP, so no issues there. But the challenge is relatively simple when you just describe it. You just fetch the list from the remote server, and you have the list on your local server. And you just have to synchronize them. Whatever has been removed, you remove. Whatever has been removed but it's being used, you basically mark as deprecated or outdated. And whatever came from the server, you just need to add. All right. So relatively simple task, but the challenge actually was in those little gotchas. So yeah, you fetch the data from the remote server, but the remote server will fail with timeout 50% of times. Just to make your life a little more interesting. The list that you receive is paginated. So you get with each request with each response that you get the link to the next page. But to make it more interesting, the last page will also give you a link, but it will give you a link to some dummy site. So if you're not careful, if you're just trusting that link, without checking whether this is actually a link to the next page, then you get dummy data, right? So a lot of challenges like that, plus efficiency concerns. You get 50,000 entries that you gotta insert in the database and do it efficiently. Compare those lists, so you need to design some kind of hash map or some kind of lookup table to just quickly assess whether the entry is there or not. It basically needs to work efficiently, plus unit tests, and that's pretty much it. So this probably wouldn't have been a big challenge if I have been doing that on the daily. But it took me a long time, or a lot longer, because I had to figure some stuff out. And first time I deployed the project, or I checked out the project, I was looking for Docker Compose, Docker files, and I couldn't find any. So I figured, okay, and I saw some installation scripts, some setup scripts. So I started running that manually, analyzing what they do, and then I figured that there's got to be something that I'm missing here. And indeed, there's a wrapper, the Docker Compose wrapper, or actually the Docker wrapper, called Lendo, and that's what they used. I've never heard of it before, so that's why it took some extra time for me to just even set it up. And then after setting it, I couldn't really set it up locally. I was having issues with that, and but if you set it up with Docker, you can SSH to the container and just run it from there, and that's what I did, just to go around the problem to save time. But this would not be a scalable solution, meaning my local environment would have to be adjusted so I can test it locally, so I can use Xdebug if need be. I didn't need it in this case because it was relatively simple, but in more complex problems, it helps a lot to be able to step through the code. So because I finished it last night, but I submitted it today, because yesterday I wanted, because along with the pull request, or along with the code, you need to do a good description of the pull request, and talk about all that stuff in the description of the pull request. And yesterday I was pretty tired, so I figured now I'm gonna do it today in the morning. I don't think you get any extra points for being fast, is my point. But I don't know. I have no idea. What is this? What is that for? Does it just cool down the board? Okay, where is the fuse? Is this the fuse? No, this is the filter. There's the relay. Oh, there's got to be the fuse. Yeah, it's installed upside. Yeah. This has got to be a fuse. Okay, so let's connect it through the light bulb first. See what's up. Now, if the light bulb goes off, we have a short. But since we have a relay switch over here, that's probably not going to happen. But we'll see. First, let's see if it even turns on. Then we'll check if it does have a standby. And if it doesn't turn off, if it doesn't turn on and does have a standby voltage, we have to dig the board out and do some measurements. This doesn't look like it has PFC or active PFC. It looks like it has passive PFC over here, the big transformer over here, or big coils, which is good. I mean, on one hand, it is good because PFC circuits are a lot easier than the rest of the PSU. So usually when there is a problem with PFC, that's usually prominent or easy to repair. All right, here comes nothing. Yep, the absolute nothing. And there's not even a standby. If there was a standby, this would lit up. I think it would. Now, do I remember which pin is standby? I don't think I do. But let's check this. So if it's blown fuse, we're gonna have no voltage here on the bridge rectifier. Huh. Ain't that something? Oh, right, because I'm on AC. Yeah. Okay, we have nothing on the bridge rectifier, which is a good thing. It's a good thing because that means that perhaps our fuse is blown, and maybe it's the same issue we had with the last one, just blown fuse and nothing else. It happens, but in my experience, so ignoring that last one, in my experience, the fuses don't just blow by themselves. There must have been something that happened that caused the fuse to blow, which means there was a short somewhere, or there is a short somewhere still on the board, and that blew the fuse, and now we have to find the short. I'm not worried since there's no voltage on the bridge rectifier. I'm not worried about being electrocuted by the caps, but if there was voltage there, we would have to be careful here to discharge the caps. I mean, it's not going to kill you, but it's very unpleasant when the cap discharges through your body. I got electrocuted. So either my measurement was wrong, but I got electrocuted here somewhere. Huh. I don't know, either my measurement was wrong, so we can probably check it on this side now. But either my measurement was wrong or the caps held the charge for this long, you know, since it was working before. In either case, that is relatively weird. Okay, here's our fuse. So let's check this baby first. The fuse seems fine, unless I'm checking the wrong thing, but I don't think so. Yes, the fuse seems fine. So probably my measurement was wrong on the what do you call it, on the bridge rectifier. Now with a better access to it, let's see that again. So this is yeah, okay, we have well, that is too bad, but alright, we have 160 volts on the rectifier, so this is fine. Now let's check for standby, but I forgot which pin. And we have standby. So that is not good. We have very nice stable 517 on the standby. That is not good because that usually means that there is a deeper fault that is very difficult to diagnose. That was not the best option. I should have used a lot higher resistance than 2 ohms. But, you know, back in the day we used to just do it with the screwdriver. It worked. Okay, so we are not turning on. So first thing that we need to identify is the standby. Well, we know the standby works, right? But now we want to see if the standby makes it to the chip, the control chip, the main control chip, which is going to be on the secondary. And that chip not working would explain why it's not starting. Now, the negative 12 volts is stabilized by 7912 regulator. Interesting. I mean, I see that often on the PSUs. So very poor access. Very poor access to everything. So we have 3 transformers, right? One is our main transformer, which pumps the entire power. One of these 2, we don't know which one, but one of them is a standby transformer. That's what produces our 5 volts to supply the logic on this side. The other one is a control transformer, which connects to the transistors, and our secondary side actually controls these transistors on the primary side. So that's what pumps our energy. We have 2 transistors over here, so we don't hear the relay clicking. That could be explained by shorted transistor. We have kind of low reading here. Much lower than here. But in the kilo ohms, so that's probably not our issue. We have some kind of chip over here on the primary side, and we have some control chip, some control logic here. And this is our secondary side. So no clicking means that it's not even trying to boot. It's not even trying to start. So probably this is probably not a feedback issue. What are these? These don't look like diodes. It's very hard to read this board. Let's see if we have some shorts on the output, because output shorts could explain why it's not working. But there's no shorts on the output. But it's nicely labeled. Everything is nicely labeled on it. Let's see, 3.3 is fine. 5 volts is fine. That's the ground. That's the ground. Unfortunately, all the cables are black, so it's kind of difficult. Oh no, never mind. I was touching the wrong thing. I thought there was a short on 12 volts. No, everything's fine here. So no usual faults. This has got to be our heart, our control circuit over here on this tiny board. So this might be our fault. This is just output. So if there was a problem with this, we would hear the click. And since we don't hear the click, it's not even trying to boot. Let's see what IC8 is. PS2 4224. This is power or reference voltage. Well, it can be used as a reference voltage. It can be used as a current limiter in various applications. Blah, blah, blah. But we want to see a data sheet for it. 4-channel secondary monitoring IC. Okay, looks like the manufacturer of this is not keen to share the information what's inside, or at least not for free. That's weird, but okay. This is unlikely to be our culprit, because first there needs to be a signal to our transistors to start switching, to start producing voltage. That's when this chip would kick in. Well, let's see if we can figure out. Probably not, but let's try anyway. The relay how is the relay controlled? Ah, crap. So these are the relay. Yeah, there's a little diode over there. So that's what controls our relay. Now, this is probably the ground. Let's confirm. We're on the hot ground. So this should be nope. Oh, this is going to be a nightmare. Let's see, this line, yeah. So it comes from this circuitry over here, right? So this is what turns on the relay. It is on secondary side, which makes sense. And there's our control chip. Now, does it control both the relay switch and the transistors? Could be. If that be the case, we should see clearly that it's going to the control transformer, whichever one of these two it might be. But can't really see much over here. Yeah, so the control transformer is this one. By this one, I mean that tiny one. So this bigger one over here is a standby. We can quickly confirm that too. And our control signal comes from here to the transformer, these two pins, and these two are for these two transistors. This one and this one. So these are our main transistors, and they are in front of our main transformer. So that's what produces our voltage, right? No shorts on these. So we just are not turning on. Now, shall we check if the relay is actually working? should be control. Let's give it 4 volts. Let's see if it's gonna be clicking. I'm not sure about the polarity, but what we do know is that the diode is gonna be in reverse here to discharge the coil. This is weird reading that I'm getting here. Very weird reading. We have no marking on the diode. I would think this is the ground. There should be a transistor somewhere that controls it, but I guess the transistor is on this board over here. Oh, maybe this is the one. Yeah, this is the one. Yeah, so this is the ground. But in that case, why is this? Why is this connected here? So that would look like a control signal. It's very hard to read this board because there's plenty of markings and stuff. Okay, it connects here, and from here it connects here. So this is our pin that I expect would go high. Let's see if we can clean this diode and see the polarity of the diode. Because if the diode is in the circuit and I connect it in wrong direction, you know, nothing's bad gonna happen to the relay. Relay can pretty much work in either direction, but this diode makes it polarized, and it needs to go in a good direction. Otherwise, all the energy is going to go through the diode and potentially damage it. Oh, I think I see it. Yep. The positive is here. Nope. I'm not sure now. Oh no, there you go. Okay. Yes. So the positive is on the left. Okay, let's connect and see. Yeah, and the relay is not clicking. Could it be the... Let's read what the relay says, because maybe it's like 12 volts or something. And there's nothing on the relay. Well, at least not at the top. It's on the side. Yeah, it looks like it's 12 volt. I would think that 12 means that it's 12 volts, 1 amp, 12 volts. And the output is 10 amps, 250 volts. So, let's try again with higher voltage. We just want to hear the relay click. Now, in some cases, relays might click, but still not conduct. That happens sometimes, but that's not an issue here because it's not clicking. Yeah, I heard a little click. It's grabbing 0.8 watts, but it didn't click down. But now it clicked down. So it's on the self-latching mechanism or circuit. It's on, and it stays on for as long as and now it turned off. So we know that we need to receive a 12 volts over here for the PSU to turn on, to actually start delivering power. Now what we could do is either bridge or manually turn on the relay to confirm. Well, actually, what are we going to confirm with that? Not much. But yeah, because without that, the chip is not going to start cycling. It's not going to start switching transistors. So we know that our fault has got to be on this little board. The readings that I get on all these diodes are weird. Oh, this one's actually reading fine. But the one on the, what do you call it, on the relay switch is acting weird. But that is, that is to be expected when you measure in circuit. To reliably measure the diode, it's best to just remove it from the circuit. Now here we have more transistors, S and D transistors. Which are fine, at least not shorted. And this one is showing weird. What are these transistors for here? So now it would be beneficial to have a schematic. But that's not something we will have. Not for this one. I mean, I can look for it probably, but probability I will find the schematic to this exact revision is slim to none. what is the component here? Well, it's jumper. So we're jumped to here. And what is this? No idea, because it's behind everything. Oh, that's another 3 jumpers here. Okay, another 3 jumpers jumping here. It's gonna take hours just to reverse engineer this circuit, just to even run some tests. I know. I'm not replacing caps for 2 reasons. First of all, it's a bit too new to be suffering issue from the issue of dry caps or high ESR. Can we check ESR? Sure, we can check, but for the ESR to give us an issue, first this relay needs to turn on. If the relay doesn't turn on, that's not where our issue is. And actually, let's check this. So the relay, it seems clear that the relay this is the positive, right? This is the negative, through the 0 ohm resistor to the collector of the transistor. Would this be the base? We have 0 going here and here. Oh, 2R. Oh. Okay. So we've got something here. So we go here, yes, through 0 ohm resistor. No, none of these. Oh, this one? No, not this one. So we need to trace this. Where does it go? It looks like it goes underneath this guy. Oh, to this guy. And it disappears. Who knows where? So it kind of looks like this chip is actually going to turn on the relay, but I can't find the connection. We know it's this resistor, but since the board is painted, we don't know where this goes. Not to any of these. Well, there's one more thing that we can check. So if my assumption is correct, and it seems correct, that this transistor operates the relay, this should be ground. Doesn't seem like it, but yeah, this is ground. Okay, so if this is ground, that means this is the emitter, which makes this a collector and makes this a base. So if that is true, and it can't be any other way, that means we need to have 12 volts over here for the relay to turn on. And how would we have 12 volts here? Where from? Ah, crap, I was using the wrong measurement. Again, is this ground? It is not. Okay. Okay, good thing I checked, because, yeah, this is not ground. This is ground. Okay. So, 10K. So we're operating this relay through 10K resistor. It doesn't make sense, especially since we have a cap over here that goes to ground. So no, I think my assumption is wrong. But let's check it anyway. So if that be the case, we should have voltage over here always, and it's controlled by the transistor. So let's see about that. And actually I have one more thing that I can check. One more thing that I can check is connected through no light bulb, although it would be very, I mean, yeah, I've seen that before. Like if you connect it through the light bulb, it doesn't work. You connect it through the, without the light bulb, it does work. It happens. So now we want to see some voltage over here. And we have none. Yeah, it's completely dead here. So for this to work, we should have a voltage here. It's prompted to boot and check again, not that it should matter, because that voltage should be there in either case. We have plain 0, so that is, oh, hang on, is it on? Okay, it was not on. That explains it. Well, we have 43 millivolts. So that would be like, no. That's too low. But let's do final test without the light bulb. So we know it doesn't blow, so we can connect it without the light bulb. And still nothing, as expected. Let's check the voltage here, and it's at 48 millivolts, 49, 50. So without voltage here, it will definitely not turn on, even if we're trying to turn this one on. So, but we have some voltage here. Now it's 60 millivolts. Nothing on this side. So I think it is trying to turn on. So this goes to ground. Over here, that's ground. Yeah. So we don't know if this is NPN or PNP. Because if we had 5 volts here, or some voltage here, what the? 12 volts is spiking. What is going on here? Yeah. Our 12 volts is jumping from around 8 to 10. Our 5 volts is spiking. Our 3.3 is spiking. But why did it turn on now? That is so weird. It's the first time I see something like that. So after measurements, it turned on. So the relay turned on. Now the relay, the voltage on the relay is jumping from 10 to, yeah. What do you think this is? Cups. Let's see, it's turned off. Because the slow start could be explained by cups. Fluctuating voltage also can be explained by cups. cold solder. It also could be explained. Well, looks like we have, so first circuitry or first voltage is the standby. Our standby transformer is probably also creating that 12 volts, because where else would it come from? Are we boosting 5 volts to 12 volts for the relay? Unlikely. In some cases, no, that's probably not it. So looks like I booted it with the measurements. So if I connect it somewhere here, I triggered something to boot it, turn it on. I don't think this is CAP's issue. Doesn't feel right. And I don't see 12 volts on the standby transformer. Oh no, there it is, 17 over here. Yeah, so the standby transformer produces 2 voltages. Where are you? Over here. Alright, so our first voltage is here, which is 5 volts on this pin. This is ground, and this is, well, 17 and some volts. Right, and that goes to our control circuit, this pin. So this is our 12 volts supply, and now that 12 volts should be going here to turn on or to supply voltage to the relay switch, and we have only 52 millivolts. So if I short this, it turns off. It turns on. Our 12 volts is high, and our negative 12 volts is high, and our 12 volts is low. 3.3 is fine. So this is basically the issue here, right? We don't have the voltage over here, but that doesn't mean that this is the fault of the circuit. See, now we have 300, 200 millivolts because it's discharging. But it did boot a little, right? And it did work showing low voltages. Now it's showing high voltages. Let's see how high. Let's short this again. So we have 5 volts. That's good. And we have 14 volts on the 12 volt. So we're 2 volts above. Well, we have something to look for. Oh, and right, because okay, that explains it, because I'm pushing 17 volts over here instead of 12. It should be 12 volts. So that could explain why the 12 volts is high. But I'm gonna stop here because I'm tired. At least we know what the issue is. I really don't think it's the cap issue, but I do not eliminate it yet. It still could be a cap issue. But what we do know is that this board is not functioning as intended. It's not producing 12 volts to the, for the relay. So this is our point of interest. So next step would be to remove that board, that sub board from this board, and analyze it. Slightly reverse engineer it. But that's gonna be, well, it's quite a project. I was hoping this would be some kind of simple fault, but it looks like it is not. Or maybe it is simple fault, but as you can see, it's gonna take a while to actually find it. I'll see if I'll come back to it tomorrow. It all depends. But in either case, thank you guys very much for watching. I do appreciate you. Hope you found this useful, and I shall see you in the next one.